Hello and welcome to Lecture 2 of our Mathematics 2 course. Today we're going to finish Chapter 8. We will talk about using trigonometric substitutions to do some integrals. We'll do integration of rational functions by using partial fractions, and we'll talk about improper integrals. Can anybody hear me? Okay, if you're having problems, try fiddling with your settings, try disconnecting and reconnecting. I'm going to start by talking about trigonometric substitutions, using trigonometric substitutions to calculate some integrals. And this section is based on these three triangles. We're going to pick two sides of a triangle and call them A and X, and then we use Pythagoras to define the other side, to define the blue side. Let's look at this triangle first of all. We'll call the base x, the height x, and then the hypotenuse, of course, is square root of a squared plus x squared. X and a are connected together using the formula x is equal to a tan theta. So a squared plus x squared is the same as a squared plus a squared tan squared theta. Or a squared 1 plus tan squared theta. And you will recall we had an identity from last week. That's the same as a squared sec squared theta. Now, we don't want to be thinking about any theta. We just want to be thinking about theta between minus pi over 2 and pi over 2. That will give us all of the possible values of x. And if we are between minus pi over 2 and pi over 2, then sec theta is always positive. So we don't need to worry about absolute value signs when we do our square root. We could write that the square root of a squared plus x squared is the same as a sec theta. And this is the substitution we're going to be using. If we see something like square root of a squared plus x squared in an integral, we're going to replace that with a sec theta. Let's look at the second triangle. This time I choose the height and the hypotenuse. I'm calling these x and a. And then the blue side is just given by square root of a squared minus x squared. Here, x is equal to a sine theta. So we can substitute this in at the bottom. A squared minus x squared is a squared minus a squared sine squared theta, which of course is just the same as a squared cos squared theta. Now, as again, we're interested in the middle part of the graph. We're just interested in theta between minus pi over 2 and pi over 2. That will give us all of the values of x that we need. And if we are between minus pi over 2 and pi over 2, then cos theta is always positive. So again, we can take the square root of this equation, and we just get square root of a squared minus x squared is a cos x. No need to worry about absolute value signs here. This is a substitution we're going to be using later. When we see square root of a squared minus x squared inside an integral, we're going to replace that by a cos x. And the third and final triangle looks like this. This time I'm going to call the hypotenuse x and the base a. And then x is a sec theta. Just as we did before, let me fill it in. Now, x squared minus a squared is the same as a squared tan squared theta. Now, this time I don't want to be between minus pi over 2 and pi over 2 because that would only give us positive x. I want all the possible values of x. So I'm going to be looking between 0 and pi over 2 and between pi over 2 and pi. If theta is between 0 and pi over 2, that's the same as saying that x is greater than or equal to a. If theta is between pi over 2 and pi, that's the same as saying that x is less than or equal to minus a. And this time, because sometimes tan is positive and sometimes tan is negative, we do need to put in absolute value signs. We'll worry about if this is positive or negative later. So let's just recap what I've talked about. We have these three substitutions that we're going to be using. If we see a square root of a squared plus x squared, we use the left one. If we see square root of a squared minus x squared, we'll use this middle substitution. And if we see square root of x squared minus a squared, we'll be using this substitution on the right. For example, find the integral of dx over the square root of 4 plus x squared. That sort of looks like the left one, the square root of a squared plus x squared. So this is the one we're going to be using. We're going to let x be equal to 2 tan theta. Then dx is 2 sec squared theta d theta, and the square root of 4 plus x squared, using the formula from up here, must be 2 sec theta. Okay, now I'm ready. I'm going to substitute these into the integral. I replace dx by 2 sec squared theta d theta, and I replace the square root of 4 plus x squared by 2 sec theta. And these terms are going to cancel. This is just the same as the integral of sec theta. This substitution has changed our integral into an easier integral. This is one that you know. You should have done this in Mathematics 1. The integral of sec theta is the natural logarithm of the absolute value of sec theta plus tan theta plus c. And then finish by doing the substitution again. That's the natural logarithm of the absolute value of square root of 4 plus x squared over 2 plus x over 2 plus a constant c. The end of this, you know how to do this. What is new here is doing the substitution. Doing the substitution, x is 2 tan theta, to change our integral into a nice easy integral. Let's do another one. Calculate the integral from 0 to 3 over 2 of dx over the square root of 9 minus x squared. Which of these three substitutions should we use? The left one, the middle one, or the right one? So in our integrand, we have the square root of 9 minus x squared. That looks like the square root of a squared minus x squared. So I'm going to be using this middle substitution. So what I do is I start my answer by saying, let x be 3 sine theta. Then we can write down that dx is 3 cos theta d theta, and the square root of 9 minus x squared, using the formula at the top, is the same as 3 cos of theta. There's one more thing we need to do here. We need to take care of the limits of integration. If x is 0, then theta is inverse sine of 0 or 0. If x is 3 over 2, then theta is inverse sine of a half, which is pi over 6. That's all the information we need. Now we can do the substitution. Our integral is the same as the integral from 0 to pi over 6. 3 cos theta d theta divided by 3 cos theta. And this is very, very easy. There's another way to calculate this. If you remember that the derivative of inverse sine of x over 3 is the same as 1 over the square root of 9 minus x squared, then you could do it directly like this. Let's look at an example from the book. We did this integral before. We've seen that we did this with a number in, but we did this basically the same. The integral of dx over the square root of a squared plus x squared is the same as the natural logarithm of the absolute value of, etc., this function. But inverse sine of x over a is also an antiderivative of 1 over the square root of a squared plus x squared. So the difference between these two functions must just be a constant. This tells us that inverse sine of x over a must be the same as this term, natural logarithm of the absolute value of the square root of a squared plus x squared over a plus x over a plus a constant. But what is this constant? We can find the constant by putting in x equal to 0. On the left side, we would have inverse sine of 0, which is just 0. We change color. If we put 0 here, this is just 0. If we replace x by 0, this is 0, forget about that. This is 0. We will get square root of a squared over a, or just 1. Natural logarithm of 1 is 0. So we would must have that the constant is equal to 0. That proves that this formula is true. I was deliberately very quick there. You can reread that example in your textbook later. Let's move on. Calculate the integral of x squared dx over the square root of 9 minus x squared. Now again, we have an a squared minus x squared term here. That tells us that we want to be using sine. So we let x be 3 sine x, just as we did 2 examples ago. And then dx must be 3 cos theta d theta. And 9 minus x squared is 9 cos squared theta. We could in fact put a square root in here because, as we said, everything here is positive, so we can just take square roots and not worry. So substitute all of this in, and it simplifies to this. It simplifies to 9 multiplied by the integral of sine squared theta d theta. You know how to calculate this integral, so I'm just going to skip to the next example. Please do read this example in the textbook and check the details. Calculate the integral of dx over the square root of 25x squared minus 4, where here we insist on x is greater than 2 over 5. First thing to do is to rearrange this so that we have some of the standard form. I want to have something which looks like square root of x squared minus a squared. So just a quick rearrange first. This looks like the third substitution, the one I was writing on the right. So we need to let x be 2 over 5 sec theta. We can calculate dx, and then we can substitute into the integral. Let's see, what are we doing here? Yes. Okay, so here's dx. And then on the bottom, the 5 square root of x squared minus 4 over 25. When we do the substitution, we replace this by 5 multiplied by 2 over 5, tan theta. And most of these terms are going to cancel. Tan cancels with tan, 2 over 5 cancels with 2 over 5. We're just left with sec theta over 5. So we're left with an easy integral. I'll skip ahead. So as I said last week, I have quick examples and I have slow examples. Slow examples, I'm going to try and give all the details. Quick ones, I'm just looking at them from the book. I'm going to pick out the key points, but I'm relying on you rereading these examples in the book at a later time. Let's move on to the next section. That was all of the ideas from 8.4. We're looking for square root of a squared plus x squared, or a squared minus x squared, or x squared minus a squared. And then we're doing the substitution to change our integral into an easy integral. All the examples in that section are basically the same. Now let's talk about partial fractions. If I said, right, 2 over x plus 1 plus 3 over x minus 3 is equal to something over something, you know how to do this. We put everything over the same denominator. The first fraction, we're going to multiply on the top and on the bottom by x minus 3. And the second term, we're going to multiply on the top and on the bottom by x plus 1. And then we can simplify that to 5x minus 3 over x squared minus 2x minus 3. But what about if we want to go in the opposite direction? What if we start with a rational function, and I ask you to write this as something over x minus 3 plus something over x plus 3? What do we do? Let's do this one again. Let's look at 5x minus 3 over x squared minus 2x minus 3. I want to write this as some number a over x plus 1 plus some number b over x minus 3. And for the moment, let's just pretend that we don't know the answer. Let's pretend that we don't know that a needs to be 2 and b needs to be 3. How could we find a and b? Well, we do basically what we did before. We start with a over x plus 1 plus b over x minus 3. First term, we multiply on the top and on the bottom by x minus 3. The second term, we multiply on the top and the bottom by x plus 1. And then we're going to be simplifying this. That's ax minus 3a over x squared minus 2x minus 3 plus bx plus b over x squared minus 2x minus 3. Or a plus bx plus b minus 3a. And this needs to be the same as the function that we started with. A plus b needs to be the same as 5, and b minus 3a needs to be the same as minus 3. So we have these simultaneous equations. You should know from high school how to solve these. Solving these, we find that a must be 2 and b must be 3. We can use this technique on a rational function, f of x over g of x. That's a polynomial divided by a polynomial. If the degree of f is smaller than the degree of g, and if we know how to factorize g. Let's do some examples. Write x squared plus x plus 2 divided by x plus 1 multiplied by x squared plus 1 in partial fractions. So we start with two terms. I have an x plus 1 factor here, so the first one should be something over x plus 1. And I also have an x squared plus 1 term, so the second term should be something over x squared plus 1. But what are the somethings? The somethings should always be a polynomial which is 1 degree smaller than the denominator. Here, x plus 1 is a first degree polynomial. So on the top, I should have a 0 degree polynomial. A 0 degree polynomial is just a number. In the second term, on the bottom, I have a second degree polynomial. So on the top, 1 less than 2 is 1. I must have a first degree polynomial, or number x plus number. Now we need to find a, b, and c. So we put everything over the same denominator. First term is multiplied on top and bottom by x squared plus 1. Second term is multiplied on the top and the bottom by x plus 1. Multiply out and then simplify. We get a plus b x squared plus b plus c x plus a plus c over x plus 1 x squared plus 1. And this needs to be the same as the function that we started with. So let's compare the terms. Here's an a plus b x squared and here's a 1 x squared. So a plus b must be equal to 1. Then I have b plus cx and 1x. So b plus c must be equal to 1. And then finally, I have an a plus c and a 2. So a plus c must be equal to 2. Here's a simultaneous equation of 3 equations and 3 variables. When we solve this, we find that we must have that a is 1, b is equal to 0, and c is equal to 1. So then that gives us our answer. A must be 1, so that's 1 over 1 over x plus 1. B is equal to 0, c is equal to 1, so we have 1 over x squared plus 1. That is the answer to this problem. Another example. Write 3x cubed plus 2x squared plus x divided by x plus 3 to the power 4 in partial fractions. Now this is slightly different because we have 4 factors on the bottom, but they're all the same. So what we want to do is we want to write this as a number over x plus 3, that's the x plus 3 to the power 1, and then a number over x plus 3 squared, and then a number over x plus 3 cubed, and then a number over x plus 3 to the power 4. And I'm not going to finish this example. After that, the idea is the same. If we have a power of a factor on the bottom, we need to do all of the powers in our partial fraction. For example, write 71 over x plus 3, x squared plus 2x plus 3 squared in partial fractions. On the bottom, there's 3 factors, but 2 of them are the same. There's an x plus 3, and there's an x squared plus 2x plus 3. So we need to write it like this. We need to have something over x plus 3, something over x squared plus 2x plus 3, and something over x squared plus 2x plus 3 squared. What are the somethings? The first one is just a number, because on the bottom we have a first degree polynomial. The second term, on the bottom that's a second degree polynomial, so on the top it needs to be a first degree polynomial. And then this is just repeated, another first degree polynomial. Again, I'm not going to finish this. The textbook tells us the rules here. If we have a factor of x minus r to the power m, then in our partial fractions, we need to have all of these. Something over x minus r, something over x minus r squared, and so on, all of the way up to something over x minus r to the power m. If we get something like x squared plus px plus q to the power n in our denominator, then we need all of the powers of this. So 1 power, 2 powers, 3 powers, all the way up to n powers on the bottom. And then on the top, we must have first degree polynomials. Let's move on. Use partial fractions to find the integral of x squared plus 4x plus 1 divided by x minus 1, x plus 1, x plus 3. We need to use partial fractions for an integrand like this. What are the factors of the denominator? There's x minus 1 to the power 1, x plus 1 to the power 1, and x plus 3 to the power 1. So it's going to be something over x minus 1 plus something over x plus 1 plus something over x plus 3. We need to find a, b, and c. If we put everything over the same denominator and then group terms together like this, we can see that a plus b plus c must be the same as 1. 4a plus 2b must be the same as 4. And 3a minus 3b minus c must be the same as 1. And if we solve this linear system, we get that a must be 3 over 4, b must be a half, and c must be minus a quarter. So our function is 3 over 4 over x minus 1 plus a half over x plus 1 plus minus a quarter over x plus 3. Now that we know this, we can do the integral. We can split our integral up into 3 easy integrals. 3 over 4 multiplied by the integral of 1 over x minus 1 plus a half multiplied by the integral of 1 over x plus 1 minus a quarter multiplied by the integral of 1 over x plus 2. There's a mistake here, of course. I'll fix that later. So the answer is 3 over 4 natural logarithm absolute value of x minus 1 plus a half natural logarithm of x plus 1 minus a quarter natural logarithm, and it should say absolute value of x plus 3. I usually use the letter c for the constant of integration, but I already used it earlier in the calculation, so I want to use a different letter just so there's no confusion. I'm just going to use plus k here, just so as not to use c again. Let's do one from the book. Use partial fractions to calculate the integral of 6x plus 7 over x plus 2 squared dx. The first thing to do is to use partial fractions. And I'm going to skip the details. I'm just going to jump down to the part I've put in the box. You can read the details later, and you can check that when we do partial fractions, our integrand is the same as 6 over x plus 2 minus 5 over x plus 2 squared. And this is now 2 easy integrals. Do these 2 easy integrals and we get our answer. Use partial fractions to evaluate the integral of 2x cubed minus 4x squared minus x minus 3 over x squared minus 2x minus 3 dx. Now, this time, we can't use fractions straight away because the top of our function, the numerator, is a higher degree polynomial than the denominator. The top is a 3rd degree polynomial and the bottom is just a 2nd degree polynomial. So what we need to do is we need to write this as a polynomial plus a proper fraction. And if you remember what you did when you studied oblique asymptotes in Mathematics 1, do the same calculation here. I'm going to skip the details and I'm just going to start talking about this one. Integral of 2x, that's easy. Let's not bother talking about that. Integral of 5x minus 3 over x squared minus 2x minus 3. Now we have a proper function. In other words, we have a rational function on the top. The degree is smaller than the polynomial on the bottom. So this time we can use partial fractions. And we can write this as 2 over x plus 1 plus 3 over x minus 3. But then that just gives us another 2 easy integrals, which you know how to do. So let's move on to the next slide. Use partial fractions to evaluate the integral of minus 2x plus 4 over x squared plus 1, x minus 1 squared dx. So what do we have on the bottom? We have one factor of x squared plus 1. So when we use partial fractions, it's going to be something over x squared plus 1. And we also have 2 powers of x minus 1. So we need to have something over x minus 1 to the power 1, and we need to have something over x minus 1 squared. What are the somethings on the top? The first term, we need a first degree polynomial on the top, because on the bottom it's a secondary degree polynomial. The thing on the top must always be 1 degree less than the thing on the bottom. And then for the next 2 terms, because it's a first degree polynomial on the bottom, it's just a number on the top. Right, let's skip through the details here. Let's skip ahead to this equation. When we do our partial fractions calculation, and you can read the details later, we find that plus 1 over x squared plus 1 minus 2 over minus 1 plus 1 over x minus 1 squared. So basically now we're just doing 4 easy integrals. Okay, let's move ahead. Another one from the textbook. Use partial fractions to evaluate the integral dx over x, x squared plus 1 squared. This time we need something over x plus something over x squared plus 1 plus something over x squared plus 1 squared. So a number over x plus a first degree polynomial over x squared plus 1 plus a first degree polynomial over x squared plus 1 squared. And then there's just the same calculations, we'll skip that. And then some easy integrals, and then the answer. You can read this in your textbook, there's nothing new here. Now, if we have f of x over x minus r1, x minus r2, etc., x minus rn, where all of these numbers r1, r2 up to rn are different, then there's a quicker way to find partial fractions. And the idea is this. We're going to multiply both sides in our decomposition by first x minus 1, and then set x equal to 1, and then we'll multiply by x minus 2 and set x equal to 2, and then step 3, we'll multiply by x minus 3 and set x equal to 3. So first of all, let's multiply both sides by x minus 1, and then set x equal to 1. Now what happens is if we set x equal to 1, we get 1 minus 1, which is 0. And we get 1 minus 1, this is all 0. The right-hand side just becomes a plus 0 plus 0. And on the left side, we get a number. And in this case, the number is 1. You can do the same thing by multiplying the equation at the top multiply equation 3 by x minus 2, and then replace x by 2. The right-hand side then becomes 0 plus b plus 0, and the left side is some number. And then finally, we could multiply both sides by x minus 3 and then replace x by 3. The right-hand side then becomes 0 plus c, and the left side is some number. Let's do a slower example. Find the integral of x plus 4 over x cubed plus 3x squared minus 10x. The denominator we can factorize like this. So in partial fractions, we're going to have something over x plus something over x minus 2 plus something over x plus 5. We're going to do three things. First, we're going to multiply by x and then set x equal to 0. Then we're going to multiply by x minus 2 and set x equal to 2. And then step 3, we'll multiply by x plus 5 and set x equal to minus 5. Okay. So I've put the equation that we're using at the top. Multiply it by x. This x disappears. This x disappears. We get another x here, and we get another x here. And then replace x by 0. That's 0 here and 0 here. The right-hand side is just a plus 0, and the left side is a number, in this case minus 2 over 5. If you have a question, you're welcome to type it in the chat, or if you wish, make a note of the slide number and you can ask me at the end. Now let's do the same thing for x minus 2. Take the equation at the top and we're going to multiply everything by x minus 2. So this one will disappear, this one will disappear, we'll get x minus 2 multiplied by a, and we'll get x minus 2 multiplied by c. Replace x by 2. This is 0, this is 0. The right-hand side is just 0 plus b plus 0. And then on the left side, replace x by 2. 2 plus 4 divided by 2 multiplied by 7. Or 3 over 7. Do the same thing, but multiply by x plus 5 and then set x equal to minus 5. The right-hand side then just becomes 0 plus c. And the left side, when we calculate it, is this number. And that was quicker, that was less work than using the first method I showed you. So the partial fractions is minus 2 over 5 over x plus 3 over 7 over x minus 2 plus minus 1 over 35 over x plus 5. And therefore the integral that we're trying to calculate is one that we can do quickly. Minus 2 over 5 natural logarithm of x plus 3 over 7 natural logarithm of the absolute value of x minus 2 minus 1 over 35 natural logarithm of x plus 5 and plus a constant. Yes, I know I already used c, but I'm using it for something else now. We could also use differentiation to find partial fractions. I'm going to take a break soon, just 3 slides left. For example, find a, b, and c in this equation by clearing fractions and then differentiating and then substituting x is equal to minus 1. When they write clearing fractions, what they mean is multiply both sides by x plus 1 cubed. So on the left side, we just get x minus 1. And then on the right side, a, x plus 1 squared, plus b, x plus 1 plus c. If we replace x by minus 1, then this is 0, this is 0. The right-hand side is 0 plus c, and left side is minus 2. So then we know c. Next, I want to find b. Differentiate both sides, and we get 1 is equal to 2a x plus 1 plus b. Replace x by minus 1. First term is just 0. We can read that b is equal to 1. Differentiate again, and we get 0 is equal to 2a. So a must be 0. So then we can write the answer. One more technique. Sometimes we can just make some guesses. Sometimes we can just guess x is 0, x is 1, x is minus 1, x is 2, x is minus 2, and see what happens. For example, let's suppose we're trying to find these partial fractions. Step 1 is to clear the fractions. In other words, multiply both sides by x minus 1, x minus 2, x minus 3. And then we're going to start making some guesses. Let's see what happens. First, we can see what happens if we put x is equal to 1. And the answer is, let me simplify. Looking at this equation in the orange box, if we put in x equal to 1, on the left side we get 1 plus 1. On the right side we get 2a plus 0 plus 0. So that's an easy way to find a as 1. And then we might say, let's try x is equal to 2. What happens if we try x equal to 2? Now we get 0 minus b plus 0 on the right side, and on the left side b. So that's an easy way to find b. And then finally we can guess what happens if we put x equal to 3. Then we find 10 on the left and 2c on the right, so c must be 5. And then we get our answer. This is another technique to find partial fractions. Now let's take a break. Let's take a 10-minute break. So let's start at 5 minutes past 2. Let's continue. The final idea for today's lesson is improper integrals. The integral from 1 to 4 f of x dx, we know this represents this area. But what if instead of stopping at 4, we let the area go all of the way to infinity? What does this mean? How could we calculate an integral from 1 to infinity? The answer is we need to use limits. Calculate the integral from 0 to infinity of e to the power minus x over 2 dx. We're going to do this in 2 steps. Step 1, we're going to calculate the integral from 0 to b. And then in step 2, we're going to take the limit as b tends to infinity. And this is what an improper integral really means. Anytime we see infinity as one of the limits of an integral, what it really means is put a number there instead and then take the limit. So step 1, because the integral from 0 to b, e to the power minus x squared over 2 dx, is minus 2 e to the power minus b over 2 plus 2. When we take the limit of this, we get 2. This area, the area under this graph between 0 and infinity, is equal to 2. Okay, some rules from the textbook. If we see an integral between a and infinity, what we need to do is we need to replace the infinity by b, and then we take the limit as b tends to infinity. If we have a limit with minus infinity, we need to replace this by a letter, any letter do you want, but let's say a, and then we take the limit as a tends to minus infinity. If we have a minus infinity and infinity, then it's a little bit more complicated. We can't do this in one step. We need to split this into 2 integrals. Choose a number c, doesn't matter which number you choose, any number c, and then split the integral at c. And then we use rule number 1 and rule number 2 to calculate these 2 integrals. If this limit exists and is a finite number, a real number, then we say that the improper integral converges. And whichever value we get as the limit, we say is the value of the improper integral. If this limit doesn't exist, or if the limit is equal to infinity, then we say that the improper integral diverges. Here's another one. I have the function natural logarithm of x divided by x squared, which looks like this. I want to look at the area underneath this curve between 1 and infinity. And the question says, is this area finite? And if the answer is yes, what is its value? Step 1 is we replace the infinite limit with a letter. Let's use b again. So instead of integral between 1 and infinity, we're looking at the integral between 1 and b. Do this integral, we can skip most of the details. We get minus a natural logarithm of b over b, minus 1 over b plus 1. And then we take the limit of this. We want the limit as b tends to infinity of this function. Limit of 1 is easy, that's just 1. Limit of 1 over b, easy, that's 0. But what about the first one? How do we do the limit of the natural logarithm of b divided by b? We use L'Hopital's rule. Differentiate the top, we get 1 over b, differentiate the bottom, we get 1. And then this limit we can see is also 0. So the answer to this question is the integral converges, so the area is finite, and the value of this area is equal to 1. quick example. Evaluate the integral from minus infinity to infinity, dx over 1 plus x squared. We need to split this into two integrals. And we can choose any number that we want to split it at. We can split it at 0 or 77, minus pi, we can split it at 1,000,000, any number that you want. The book says that they want to split it at 0. That's sensible. 0 is a nice place to split it at. And then we have two integrals to calculate. We're going to do these two separately. First, we'll do the left one. Integral from minus infinity to 0. We need to replace the minus infinity by a letter. It doesn't matter what letter you choose to use. This book likes to use the letter A, so choose A. And then we calculate the limit as A tends to minus infinity. Skip through the details. The answer is pi over 2. And then we have the right integral. Replace infinity by a letter. The book likes the letter B. And then calculate the limit as B tends to infinity. And again, I'm going to skip through the details. You can check that this is pi over 2. So put these together, we have pi over 2 plus pi over 2, or pi. Moving on. We repeat, when we're doing the integral from minus infinity to infinity, we need to split these into two. And we can split them at any number C, any number that you want. This is not the same as the limit as b tends to infinity of the integral from minus b to b. Be careful here. You have to split it up into two different integrals. Otherwise, you're going to get the wrong number. For example, the integral from 0 to infinity, 2x dx over x squared plus 1 diverges. That tells us that the integral from minus infinity to infinity, 2x dx over x squared plus 1, also diverges. If at least one of these two integrals diverges, then the left-hand integral must also diverge. But if we try to do it using the limit as b tends to infinity of the integral from minus b to b, we would get 0. Which is not the same as divergence. So just be careful here. If you try to do it like this, you're going to get the wrong answer. An example from the book. For what values of p does the integral from 1 to infinity dx over x to the power p converge? And when the integral does converge, what is its value? So we replace the infinity by a letter, let's say b, calculate this integral, and then we take the limit as b tends to infinity, and this is what we find. If p is greater than 1, we get 1 over p minus 1. If p is less than 1, we get infinity. So the integral converges if p is greater than 1, and it diverges if p is less than 1. Try to remember this example when we get to the last chapter. In the last 3 weeks of the term, when we're studying sequences and series, we're going to be wanting this one again. So try to remember this. What happens if p is equal to 1? If p is equal to 1, the integral also diverges, as we can see in this calculation. Again, replace infinity by a letter, and then take the limit, and we get infinity. I'm going to write this as a theorem because this is one we're going to be needing later in the course. Integral from 1 to infinity dx over x to the power p converges if p is strictly greater than 1, and it diverges if p is less than or equal to 1. In particular, we're going to be using p is 1 and p is 2. If we have the function y is equal to 1 over x, this area is infinite. If we have y is equal to 1 over x squared, this area is a finite number, and in this case 1. It might seem a little bit, you might be a little doubtful of this looking at the pictures, because the area I've shaded blue here doesn't look that different, and yet the one on the right is 1 and the one on the left is infinity. The key is how quickly does the graph go down to 0 as we go to the right. This one goes down very, very quickly. This one goes down slowly. So this is why one is finite and one is infinite. What can we do if we have areas which go all of the way up to infinity? It goes all of the way off the slide, up at the top, goes all of the way up to infinity. How could I calculate the integral from 0 to infinity of dx over the square root of x? 2 steps. Step 1, instead of 0, we're going to replace this by a letter a. We can calculate the integral between a and 1, and then we can take the limit. In this case, the limit as a tends to 0 from the right. So that's the idea. Integral between a and 1, we can calculate 2 minus 2 root a, and then take the limit as a tends to 0 from the right. We get 2. Let's look at the rules that are written in the textbook. First one is one we've just done. If we have a continuous function on the half open interval between a and b, where it's discontinuous at a, then what we need to do is we need to replace a by a letter, let's say c, and then we take the limit as c tends to a from the right. If x is continuous on the half open interval between a and b, where it's discontinuous now on the right hand side, discontinuous at b, we do basically the same thing. We replace b by a different letter, let's say c, and then we take the limit as c tends to b from the left this time. And rule 3, if f is discontinuous at point c in the middle, so it's continuous between a and c, and it's continuous between c and b, but it's not continuous in the middle at c, then we need to split this up into 2 different integrals, and we'll deal with them separately. For example, investigate the convergence of the integral between 0 and 1, 1 over 1 minus x dx. This integral is continuous between 0 and 1, but it's discontinuous at 1. So what we need to do is we need to replace the upper limit 1 by a letter, in this case b, and then we'll take the limit as b tends to 1. And in this case, b tends to 1 from the left. But other than that, there's nothing new in this example. So let me move ahead. Evaluate the integral between 0 and 3 dx over x minus 1 to the power 2/3. Now, this time, our function is continuous between 0 and 1, and it's continuous between 1 and 3, but it's not continuous at 1. It has a vertical asymptote at 1. So what we need to do is we need to split our integral up into 2. We're going to do the integral between 0 and 1, and we're going to do the integral between 1 and 3. And we're going to do these two separately. So very, very quickly, between 0 and 1, replace 1 by b and then take the limit. We get 3. And again, b very, very quickly. Again, it's discontinuous at 1, so we replace 1 by a letter. Let's call it c. And then we take the limit as c tends to 1. In this case, c tends to 1 from the right. And we get 3 multiplied by the cubed root of 2. Add these two numbers together, we get our answer. I'm going to move on. Sometimes we can't evaluate an improper integral, but we can still determine whether it converges or diverges. For example, does the integral from 1 to infinity e to the power minus x squared dx converge or diverge? We can't calculate the integral between 1 and b directly because this is non-elementary, but we can answer this example another way. What we can say is, because e to the power minus x squared is always positive, I of b, that's the integral between 1 and b, e to the power minus x squared dx, is an increasing function of b. When b gets bigger, this integral gets bigger because the integrand is always positive. So there's two possibilities when we take the limit. Either the limit is infinity, either the integral keeps getting bigger and bigger and bigger and bigger as b increases, or this limit stops getting bigger and it becomes a finite number. So either this limit is infinity or the limit is a finite number. I'm going to prove to you that, in fact, this limit is a finite number. Look at the two functions, e to the power minus x squared and e to the power minus x. Now, for every b, I'm saying that the blue area is smaller than the red area. That should be clearer from the graph. The red area is minus e to the power minus b plus e to the power minus 1, which is smaller than e to the power minus 1, and e to the power minus 1 is approximately 0.36788, something. So for all b, this blue area should be smaller than 0.36788. And that means that if it's always smaller than a number, it must converge to a finite number. What I did was I took my difficult integral, which I couldn't calculate directly, and I compared it to an easier integral. The easier one we knew converge, so therefore the difficult but smaller one must also converge. That's the idea behind this theorem. Let's suppose we've got two continuous functions. There's a small function called f and a big function called g. If the integral of the bigger function converges, then the integral of the smaller function also converges. We can turn that around. If the integral of the smaller function diverges, goes to infinity, then the integral of the bigger function is bigger than something which goes to infinity. That must also go to infinity. That must also diverge. This is called the direct comparison test. I'm not going to prove this to you. You can read the proof of this in your textbook. Let's look at some examples from the textbook. First of all, integral between 1 and infinity, sine squared x over x squared dx. That's a complicated integral, but this is smaller than 1 over x squared. And the integral of 1 over x squared converges. Because the integral of the bigger function converges, that means the integral of the smaller function must also converge. This is sort of like the sandwich theorem, if you remember that from Mathematics 1. Example B. In example B, we have that 1 over the square root of x squared minus 0.1 is bigger than 1 over x. And we know that the integral of 1 over x diverges. We have a function which is bigger than a function which diverges, so it must also diverge. And then finally, part C. The inequality here is that cos x over root x is smaller than 1 over root x. The integral of the bigger function converges. We can calculate this. So by the theorem, the integral of the smaller function also converges. We have another theorem. The previous one was the direct comparison test. This one's called the limit comparison test. Again, let's suppose we have two continuous functions, and let's suppose they're always positive. The key condition here, let me put it in red, the key condition here is that the limit of f divided by g exists, and this is a finite number which is strictly between 0 and infinity. Doesn't matter what the value it is, as long as it's between 0 and infinity. Then the conclusion is these two integrals either both converge or they both diverge. To say that again, if the limit of f over g exists and is between 0 and infinity, then these two integrals behave the same. They either both converge or they both diverge. Show that the integral between 1 and infinity dx over 1 plus x squared diverges by comparing it to the integral of 1 over x squared. There's a mistake here. There must be a mistake. This should have been converges. Because if you recall, 1 over x squared converges. So the example should say, show that this first integral converges by comparing it to the integral of 1 over x squared. I will fix that later. Here's these two functions. We're going to be using the limit comparison test. So we're going to be looking at the limit of f divided by g, the limit of one function divided by the other function. Let's suppose we look at the limit of 1 over x squared divided by the limit of 1 over 1 plus x squared. But it doesn't matter which one we put on top and which one we put on the bottom. When we do the limit, we're looking at what happens at the end here. Do they behave the same when we go to infinity? And in this graph, it looks like the answer is yes. It looks like as we go to infinity, these two graphs are becoming closer and closer together. They're behaving the same way. But let's calculate this. Here's a screenshot from the book. I'm interested in calculating the limit of f over g. And really, it doesn't matter which function is f, and it doesn't matter which function is g. It could be f over g, g over f, it doesn't matter. One function on the top divided by the other function. And this time, when we calculate the limit, we get a number 1. The limit exists, and it's between 0 and infinity. That tells us that either both integrals converge or both integrals diverge. We already know that one of them converges, therefore the other one must converge as well. Now, before I move on, let me just point out the theorem tells you that they both behave the same. Either they both converge or they both diverge. It doesn't tell us anything about their values. It doesn't say that the values are the same. And in this case, the values are not the same. There's no reason to think from this theorem that the values should be in any way connected. All it tells us is either they both converge or they both diverge. Investigate the convergence of the integral between 1 and infinity, 1 minus e to the power minus x over x dx. So we're going to look at the integrand. The integrand is 1 minus e to the power minus x over x. What's a simpler function that we can compare it with? A simpler function is probably going to be 1 over x. Now, we can't use the direct comparison test because then the inequality would be the wrong way round. We know that the integral of 1 over x diverges, so we would want to use that to show that something bigger than 1 over x also diverges. But here, the inequality is the wrong way round. 1 minus e to the power minus x over x is actually smaller than 1 over x. So we can't use the direct comparison test. That's not going to work. So we use the other one. For this example, we're going to use the limit comparison test. So what we want to do is we want to calculate the limit of one function divided by the other function. And it doesn't matter which function we put on the top and which function we put on the bottom. All we want to find is that there exists a limit and that the limit is between 0 and infinity. So we do this calculation and again we find 1. We just say there's nothing special about the number 1 here. It's just a coincidence that the examples the book are choosing are giving 1. We could have any number here between 0 and infinity. It doesn't have to be 1. Because we get a number that's between 0 and infinity, the two integrals must behave the same. Either they both converge or they both diverge. We already know that one of these integrals diverge. That means that the other one must also diverge. And I'm going to finish today's lesson just by doing some recapping, just some revision of the ideas from earlier. If we have an improper integral where there's infinity in the upper limit, what we need to do is we need to replace infinity by b and then take the limit as b tends to infinity. If we have a minus infinity in the bottom limit, again, replace this by a letter, any letter that you choose, and then take the limit as this letter tends to minus infinity. If we have both limits, a minus infinity to infinity, we must split this up into two different integrals. We can't do this in one step, we have to split it into two. You don't have to split it at 0, you can split it at any number that you want. If we have a vertical asymptote at, let's say, a number 1, replace the number 1 by a letter, and then take the limit as b tends to 1 from the left. Or in this example, again, replace the 1 by a letter, and then take the limit as b tends to 1 from the right. And finally, if we have a vertical asymptote in the middle, we have to split our integral up into two. We can't do this in one step. We must split this up into two and then calculate each one separately. And that's all I want to talk about this week. Next week, we move on to chapter 11. We'll start thinking in 3 dimensions. We'll do 3-dimensional coordinate systems. We'll talk about vectors, and we'll talk about the dot product. So completely new topics next week. No derivatives, no integrals next week. Do you have any questions? Don't worry about the deadline. The deadline for all of the homework will be one day before the final exam. So work on them when you can, but try to do them sooner rather than later. Try to do some of the homework every week. Calculators are not allowed, but you won't need a calculator. You won't be calculating lots of values in the exam. Instead, we want you to give your answer in exact form. So if you find square root of 2 or pi or whatever, then just write square root of 2 or pi on your paper. You don't need to get an actual number.